All right, today we're pulling back the curtain on AI, but we're not going to talk about code or algorithms. Nope, we're going deeper. We're talking about the actual physical hardware, the industrial scale machinery, and the huge multi-million-dollar bets that power every single piece of AI you touch. You know, AI kind of feels like magic, right? It's just this disembodied brain in the cloud. But here's the thing, it's not. It's a massive physical operation running on some seriously specialized, and I mean incredibly expensive hardware. So what's really behind the trick? What's the machinery that makes the magic happen? Well, let's dive in and find out. Okay, so the first thing you absolutely have to get is that AI isn't just one thing. It really has two completely different modes of operation. You can think of them as two distinct brains. And trust me, understanding this split is the key to, well, everything else we're going to talk about. And here's the breakdown. On one side, you've got AI training. The best way to think about this is like sending the AI to college. It's this one-time, super intense process where it just crams, learning from mountains of data. And that, my friends, is a huge capital expense, or CapEx, a massive upfront bill. Then you've got AI inference. This is the AI after it's graduated and gotten a job. It's out in the world, using its education, doing real-time work all day, every day. That's your ongoing operating expense, or OpEx. It's like the electricity bill for the AI's brain, and it never, ever turns off. So let's talk about that college phase first, the training. And let's be super clear here. Training a big AI model, like the ones behind the chatbots you use, is probably one of the most computationally expensive things humanity has ever done. The scale of the investment, it's just staggering. See this number? 38 grand. That is the price for one single high-end NVIDIA H100 GPU, which is basically the foundational brick for building an AI. Almost $40,000. That's like a new car. And here's the kicker. You don't just need one, you need thousands of. Okay, now let's zoom out a bit. You take 8 of the newer B200 GPUs and you pack them into a single server, and you're looking at this number, almost $350,000 for one box. The data centers that train the big AI models, they're just filled with racks and racks and racks of these things. The scale is just mind-boggling. And it's not just about the GPUs either, not by a long shot. It's a whole ecosystem of crazy fast hardware. You need things like Google's custom TPUs, insane amounts of special high bandwidth memory just to hold the AI models, these ridiculously fast interconnects so the chips can all talk to each other without bottlenecks, and of course, super powerful CPUs to act as the conductor for this whole orchestra. It's truly a symphony of bleeding-edge tech all working together. Okay, so after spending all that money on its education, the AI is finally ready to get a job. And that brings us to phase 2, inference. This is the part we actually see and touch every single day. This is AI out in the wild. Seriously, think about it. Every time your phone unlocks just by seeing your face, or a car's computer spots a pedestrian, or you ask a chatbot a question and get an answer back instantly, that's inference. In that moment, the AI model is taking all its schooling and applying it to brand new data to give you an answer or perform an action, like right now, in milliseconds. And here is the single biggest economic surprise in all of AI. You ready for this? While training gets all the headlines with those insane price tags, over the entire life of an AI system, training is actually the small part of the bill. For any AI service that people actually use, the ongoing cost of just running it, that's the inference, makes up a whopping 80 to 90% of the total cost. It's that 24/7 utility bill that really adds up. So if inference is where 90% of the money goes, and it's happening everywhere all the time, how do you possibly manage that? I mean, you can't exactly stuff a giant power-hungry data center into a car or a camera or a medical scanner, right? You need a totally different kind of tool for the job. And this is where a real unsung hero of the hardware world comes into play. I want you to meet the FPGA, which stands for Field Programmable Gate Array. The easiest way to think about it is it's like a computer chip made of clay. It's a blank slate. Unlike a regular chip where all the circuits are fixed forever, an FPGA's internal wiring can be changed, reprogrammed, even after it's been built. It's like hardware that you can reshape to be perfect for one very specific task. And that ability to be reprogrammed, it gives them some serious superpowers when it comes to inference. For starters, their response time is insane. We're talking microseconds. Absolutely critical when a car needs to slam on the brakes. They're also super energy efficient, sometimes using as little as 10 watts. perfect for anything that runs on a battery. And maybe the coolest part, when a new, better AI model comes out, you don't need new hardware. You just send the chip an update, and it rewires itself. It's a total game changer. And because of this, you find them in some of the most critical places imaginable. In our cars, they're the brains fusing together data from cameras and radar to make split-second decisions. In hospitals, they're building the 3D images from an MRI scan as it's happening. On Wall Street, they're executing trades faster than a human can blink. And in the world of defense, they're running incredibly complex tracking systems. These are the chips you call when you need a specialist. Okay, so that brings us to the big picture, the business side of things. Who's making these specialized chips? And more importantly, how do companies make these massive, multi-million-dollar decisions about which piece of hardware is the right one for their AI product? Well, when it comes to FPGAs, the market is pretty simple. It's basically a two-horse race. You've got AMD, who bought a company called Xilinx, and they have about 60% of the market. And then you have Intel, with their Altera division, holding down about 35%. Between those two, yeah, they pretty much run the whole show for these flexible, high-performance chips. But the FPGA isn't the only game in town. It has a huge rival, the ASIC. That stands for Application-Specific Integrated Circuit. Now, if an FPGA is that flexible, reshapeable brain, think of an ASIC as a custom-made key, forged to fit one and only one lock. It's completely fixed. You can't change it. But for that one single job it was designed for, it is the absolute fastest and most efficient chip possible. But, and this is a huge but, getting that custom key made costs a fortune. We're talking millions of dollars in upfront design costs, what the industry calls NRE, or non-recurring engineering. So the whole decision boils down to simple but very high stakes math. It's a break-even game. If you think you're going to sell, say, less than 10,000 units of your product, you go with the FPGA, no question. You just can't justify that massive upfront ASIC design cost. But if you're going to be shipping over 50,000 units, maybe even millions, like in a phone, well, now that huge upfront cost starts to look pretty good because the cost of each individual ASIC is dirt cheap. It's a massive strategic bet every company has to make. Do you bet on flexibility in case things change? Or do you bet on raw efficiency because you're going for massive, massive scale? And all of this leaves us with one final, and I think really fascinating question for the future. As AI gets woven into the fabric of everything, just like electricity, what is it actually going to look like? Is the future going to be run by a handful of giant, all-powerful, general-purpose AI brains sitting in massive data centers? Or is it going to be a world with a billion tiny, specialized brains, each one a little chip perfectly designed for one single job? That's the real question, and the answer is going to shape our world for decades to come.